Welcome back. Today's topic is substitution rule. This is the last section from chapter 4, and it is one of the most important methods to solve integrals of certain type of functions. Not always possible to use this method, but it's one of the very common ways to solve certain integrals. The substitution method is basically a generalization of the chain rule. So if you remember chain rule was sorry, one second. There we go. If you remember, chain rule is if f of g of x is given and we're looking for the derivative d over dx of such a function, we'll say the derivative of the outside function f prime of g of x multiplied by the derivative of the inside, g prime x. So if this function is given, by the way, you can call the g function u, and this is the same as saying f of u. The derivative with respect to u would be the derivative with respect to x of the inside function multiplied by the derivative of the outside function. So this is kind of the chain rule if we're talking about the derivative. But for the antiderivative, given this derivative, if I ask you what would be the integral of that, you should say simply it should be f of g of x, because it's going backward in the derivative and it's supposed to give us this term plus some constants. So what it says is, if you have a composition of two functions, f and g, and you have the derivative of the inside function multiplied, you can call this inside function u, and this derivative g prime dx basically represents the derivative of u, so du. And by doing this change of variable, you simplify this complicated integral into a function of a new variable, the derivative of a function of a new variable, the integral of a function of a new variable. This might be a bit complicated to understand, but let's look at an example. It would be easier through an example. Let's say you're given this example and they ask you to figure out this integral. You see there is a product between 2x and cosine x squared. And it doesn't look that easy to calculate the integral, finding the antiderivative. So what we can do is you can look at the inside function x squared and say, okay, what if I call x squared to be a new variable? Let's call it u. Okay, let me write u. I will define u to be a x squared. You might ask, why would you choose u to be x squared? Why not cosine x squared? You will see in a second. So here, if I pick this inside function x squared to be u, what do I get is simply the integral of 2x multiplied by cosine of u times dx, right? But now I cannot deal with anything in this format because I have multiple variables in dx. This doesn't make sense. So somehow I should get rid of this dx and this 2x as well, and write everything in terms of u. So what would I do is I'll figure out and say, okay, let's take a derivative, implicit differentiation. And somehow you relate both sides. What would be the derivative of left side? It would be, let's take a derivative with respect to dx. So it would be d of u with respect to dx. And the right side derivative with respect to x would be 2x. If you multiply both sides by dx, what you get is du equals 2x dx. From this point on, I'm going to skip this middle step and say, okay, if I take a derivative with respect to u, I'm going to write 1 du, which is the same as du. Derivative with respect to x would be 2x, but since we took the derivative with respect to x, I'm going to put a dx next to it. It's the same as multiplying both sides by dx and getting rid of that. Why am I doing this? Is because I want to figure out what is dx by itself. So if I want to find dx, what we get is du divided by 2x. Divide also by 2x. Okay, if I found dx by itself, and I can replace this integral, 2x is still there, cosine u, and instead of dx, I can write it is du divided by 2x. Now you notice that this 2x can cancel out, and what do we get is simply this integral, the same as cosine of u times du. And this is basically what that theorem says. It says the derivative of this inside function is given here, 2x dx. So we can call this u, this inside is u, and what is left is these two terms is basically d of u. But I'm not going to go through the theorem every time, so I'm going to go through these steps. You introduce new variable and figure out what is the relation between du and dx and solve for dx. This is always the steps. Let me erase this implicit. This is always the steps. This is called the substitution method. Substitution method to solve integrals. And we haven't solved the integral, but it's not then complicated. If they ask you what is the integral of cosine x dx, what would be the answer? The answer must be sine x plus some constant c, because the derivative of this is simply cosine x. If they ask you what is the integral of cosine u du, this is sine of u plus some c, because the derivative is with respect to u. So sine of u plus c. What is u? U, we picked it to be x squared. So this is sine x squared plus c. And this is the integral. You can check to see if this is the correct antiderivative. We take a derivative of it by chain rule, we would get 2x times, we get cosine x squared times the derivative of the inside, which is 2x, which is simply this term. So this is the correct antiderivative. Okay, so from this point on, if you want to deal with composition of functions, cosine of x squared, for example, inside the integral, you always use this substitution method. Not always it's going to work out, but if we use substitution, there is a high chance that it's going to be possible to solve this integral. Okay, here's another example. So substitution is basically trying to get rid of that backward chain rule. So you always look at this function and say, okay, what is the inside term? The inside function. The inside function in this case is 2x plus 1. So if I want to find this integral, I'm going to call the inside function u. So u would be 2x plus 1. And then I need to figure out what is the derivative of u with respect to x. I'll write du divided by dx. The right side you would get simply 2 derivative with respect to x. And again, you can write it this way. You can write it, okay, say I took the derivative with respect to u on the right side. It is a 1 du, derivative with respect to x on the left side. This 2 dx. Either way is fine, or you can write it this way and say then I'll multiply dx to both sides. Whatever you can pick. So du is 2 dx. But we want to find out what is dx. So dx would be du divided by 2. So in the integral is still there. This term, we called it u. So we have u to the power 5. Multiply by it, instead of dx, we have du over 2. We couldn't have added 1 to the exponent divided by the same exponent because it's not simply x to the power 5. But now what we have is integral. By the way, du divided by 2 is the same as 1/2 u to the power 5 du. What is this integral? The 1/2 is constant. The derivative of u to the power 5 is add 1 to the exponent divided by the same exponent, multiple, plus some constants. There is no du, there is no integral. This is it. Be 1 divided by 12 u to the power 6 plus c. And what is the u? U, we picked it originally to be 2x plus 1. So this is 2x plus 1 to the power 6 plus. This is our integral. You can always check by taking the derivative to see if I take the derivative, do I really get this inside term? And if you apply the chain rule, the general power rule, you'll get the derivative to be 2x plus 1 to the power 5. Okay, let's do more example. Here is another one. It looks very complicated, but always try to figure out, if you use chain rule, what would be the inside function and what would be the outside function. So in this case, the inside function is whatever you see underneath the square root, 1 plus x squared. I'll pick that to be u. So what is the du? It would be derivative of right side, which would be 2x dx. Again, I didn't write du divided by dx because I multiplied the dx already to the other side. And solve for dx. Dx equals divided by 2x. So I can rewrite this integral. The x in the numerator, I don't know what it is. I'm going to keep it as it is. Square root of 1 plus x squared. This is what we call du. Multiply, instead of dx, we write du divided by 2x. This is what we found. Dx is du divided by 2x. And now you notice that the x's will cancel out. Normally, after this substitution, you should end up with one variable. If you still have multiple variables, that means your substitution was not correct, or the method of substitution does not work in this way. Okay, so what is left is 1 over 2 multiplied by 1 over square root of u du. And you notice everything is in terms of u. We haven't taken the antiderivatives. We have just changed the variable, so 1/2 is still there. Instead of 1 over root u, I can write it as u to the power negative 1/2 du. Now take the integral. What would be the antiderivative? 1/2 is still there. Antiderivative of u to the power negative 1/2 is add 1 to the exponent, divide by the same exponent, plus some constancy. You can simplify. 2 multiplied by 1/2 will cancel out. So what we have is the u to the power 1/2 plus c. That is square root of u plus c. And what is u? U was 1 plus x squared plus some constant. And this is the integral. Again, you can double check your work to see if it's correct by taking a derivative and see that you get this x divided by 1 plus x squared. One more example. Integral of cosine 5x dx. Substitution. If it was cosine x dx, I wouldn't need substitution because I already know the integral of cosine x integral is simply sine x plus some constancy. This would have been sine x plus c. But if this is 5x, you cannot say this is sine 5x plus c. Because now if I take a derivative of that, then the chain rule will show up and you'll get 1/5 cosine 5x. Sorry, 5 cosine 5x. So that is not correct if you're dealing with composition of functions. So what we pick is that we let 5x to be u. So this integral is basically cosine of u multiplied by, we need to figure out what is dx. du is 5 dx. Therefore, dx is du divided by 5. So instead of dx, I write du divided by 5. Again, 5 is a constant. You can always write it as 1/5 times cosine u. I recommend writing it this way. So you know there is a constant. You have to multiply at the end. 1/5 integral of cosine u is sine u plus some constant. And this is 1/5 sine of, what is u? U was 5x plus c. This is the integral. Try to always double check by taking the derivative. For example, if I take a derivative of 1/5 sine 5x, do I really get that? If I take a derivative plus some constancy. If I take a derivative of this, do I really get cosine 5x? You can check. 1/5. Derivative of sine 5x is cosine 5x multiplied by the derivative of the inside, 5x derivative. Derivative of c is 0. Derivative of 5x is simply 5. 5 multiplied by 1/2 will cancel out and you will get cosine 5x. And you notice this is the same as that cosine 5x that we already had. This is the small f function, this is capital F for the integral. Okay, this is how you check to see if your solution is correct. But what if we have boundaries? So what if you have a definite integral? Again, if you remember, for the definite integral, you do similar thing. You always find out the integral, the antiderivative function first, then you replace the boundaries. You don't need that constancy. So first, let's assume if there were no boundaries, what would we do? We would use chain rule, because you have a composition of function square root with 2x plus 1, another function. So we'll pick the inside function to be u, 2x plus 1, and we figure out what is du and what is dx. 2 dx, dx is du divided by 2. Replace those. Here's what I'm going to do. I'm going to ignore the boundaries. I'm not going to write the boundaries. So I have square root of u multiplied by, instead of dx, you write du over 2. Okay. This is the same as integral u to the power 1/2. Sorry, 1/2 is there. This 2 is the same as 1/2. 1 du divided by 2. So 1/2 u to the power 1/2 multiplied by du. And what is that integral? That integral is 1/2 u to the power 3/2 divided by 3 over 2. Plus some constancy, but it's not necessary since we have boundaries showing up. So this would be, simplify this 2 and that, you'll get 1/3 u to the power 3/2, which is the same as square root of u cubed. And that is the same as 1/3 square root of u was 2x plus 1, so I'm going to replace 2x plus 1 to the power 3. Now that we went back to the x, I can evaluate at the boundaries, because these boundaries are correspond to the variable x. They're not correspond to the variable u. That's why I didn't write any boundaries in these cases. I waited till I changed all the boundaries. I found the antiderivative function first. This was the antiderivative. Then I changed it to x. Change it back to the x. Now I can evaluate it as those values, 0 to 4. And what would be the integral? Evaluate the function at 4. What you get is 1/3 square root of 2 times 4 plus 1 is 9. Square root of 9 is 3. To the power of 3 is 27. So you get times 27. You can use a calculator. Minus, if you replace 0, you'll get 1/3 times 2 times 0 plus 1 is 1 to any power is 1. And that is 9 minus 1/3, so 26 over 3. This would be the integral. Okay, but now there is kind of a shortcut. Instead of going back to x, you can change the boundaries right there from the original to from the variable x to the variable u. How do we do this is by given these boundaries, you can figure out the values for u. This means x value is given 4. Question is, what would be the y value? So you can figure out the boundaries for u in that case. How do we find it? We use this relation between x and u. For example, if x is given 4, what you get is u would be 2 times 4 plus 1. So that is 9. So this upper boundary, instead of being 4, turns out to be 9 for u. If x is given 0, what would be u? 2 times 0 plus 1 would be 1. So this would be 1. It would be from 1 to 9. So after we found the antiderivative, which was 1/3 square root of u cubed. Instead of replacing it back with x, I could have said this equals, at that point, instead of going back to x, I could have said let's evaluate this at 1 to 9. And what you would get is 1/3 square root of 9 cubed minus 1/3 square root of 1 cubed, which turns out to be exactly the same thing, 26/3. So it's not necessary if you're dealing with boundaries to go back to the original function, but you need to update your boundary for the variables that you're using. Instead of x, we're using u, so I update the boundary for u. I'm going to use that to do the next example. Given this integral, you notice that there is an inside function and to some power 2. So I'm going to say let du equal 3 minus 5x. du would be negative 5 dx. We can figure out what is dx. dx would be du divided by negative 5. But now, since there is boundary involved, I'm going to update the boundary as well. What would be the boundary? So if x is 2, what is u? Replace 2 for x into this equation. u would be 3 minus 5 times 2. 3 minus 5 times 2. What you get is 3 minus 10, you get negative 7. X was, the other boundary is negative 1. What is the u? u would be 3 minus 5 times negative 1. 5 times negative 1 is negative positive 5, and plus 3 you'll get 8. The integral will change to, again, I'll update the boundary because I'm using a new variable. So again, correspond to each other. Becomes 8, so the lower bound becomes 8, upper bound becomes negative 7. You do not need to change the order. Correspond to 2, we got negative 7. Correspond to negative 1, we got the boundary to be 8. And you still have 3 minus 5x is u, so this is u to the power 2. This was u. And instead of dx, we can write du divided by negative 5. du divided by negative 5. You can write it here, or you can say, okay, this is 1 instead of du. dx, I can write du divided by negative 5 here. Either way is fine. This is easier to see, so I'm going to do that. This is the same as from negative 7 to 8, 1 divided by negative 5. And instead of 1 divided by u squared, I can write it as u to the power negative 2 du. What is that integral? It is simply negative 1 over 5. The integral of u to the negative 2 is u to the negative 1 divided by negative 1. Plus some constant c, but it's not necessary since we have upper and lower bound. So from 8 to negative 7. If you do not update the boundary, you have to replace u back with whatever it was, then use the original boundaries negative 1 and 2. But in this case, it's not, I already updated the boundary, so it's not necessary to go back to x. You can simplify this, these two will cancel out, so you get 1/5. u to the power negative 1 is 1 over u. So you can combine them together, kind of write it as 1 over 5u. And evaluate it from 8 to negative 7. That is 1 over 5 times negative 7 minus 1 over 5 times 8. And that is 1 divided by 35, negative 1 divided by 35 minus 1 divided by 40. Whatever this number is, you can do common denominator and add them up. I don't really care at this point. This is just a constant. Okay, if you do not change the boundary, if you do not update the boundary, then you have to replace u back at this point with 3 minus 5x, then evaluate it at negative 1 and 2. And you imply you do not need to update the boundary in that case. You do not need to use negative 8 and 7. Sorry, negative 7 and 8. Okay, this is you notice now that we can solve a certain new types of integrals, not only the simple polynomial and trigonometric function. You can solve a composition of polynomials with trigonometric or to power certain powers. And there is an outcome for symmetric functions. There is a certain result. So let's mention that one. Suppose given a function f, suppose f is given over a symmetric interval from negative a to a. That's very important. And if they ask you to evaluate the function over that integral, so find out what is the integral from negative a to a of f of x dx. Depending on the type of function, if you're dealing with an even function or odd function, the results are different. So let's see why are they different. First, let me remind you of what would be an even function and what is an odd function. So even function, let's say we had this function f from 0 to a. Even function was saying that it should be symmetric about the y-axis. So you should get exactly the same thing on the other side. So this would be a continuation of f to negative a. Same, exact same. This was if you have an even function. How about the odd function? The odd function should be symmetric about the origin, if you remember. So if I have, let's say this function, let's check about the origin by this one. If you have this function, you get exactly something on the other side, symmetric. Something like that. From 0 to a and 0 to negative a. Okay. What is the integral of f of x dx from negative a to a? Definition of it was basically this area plus this area. So if you have an odd function, you have this odd function, this is an odd function. But you notice that you have a positive area here and you have a negative area since it's below the x-axis. And negative integral, not area. Area is always positive. So you have a positive integral and a negative integral. So if you add these two, since they are exactly the same areas, this integral must be 0. We're dealing with an odd function. So we say if you have an odd function, the integral over a symmetric boundary is simply 0. And if you have an even function, this area is exactly the same as that area. So instead of going from negative a to a, what we can do is start evaluating from 0 to a. The area you get multiplied by 2. So 2 times the area from 0 to a of the function. If you're dealing with even function, the area is symmetric, exactly the same thing. If you're dealing with odd function, then the areas are same value but opposite. So if you add them up, you will get the integrals are opposite, so you get 0. Why I'm mentioning this is sometimes the functions are too complicated and you do not want to calculate. So here I can calculate this integral from negative 2 to 2, but it would have been easier if you would have from 0 to 2 instead of getting all the evaluating it 2 values. First, what type of functions do we have? We have f of x is x to the power 4 plus 1. This is an even function because f of negative x is the same as negative x to the power 4 plus 1 is x to the power 4 plus 1, simplified version. You see that f of negative x and f of x are the same, so you have an even function. So what is this integral? Is basically the same as 2 times, it's not the boundary. Let me change the boundaries to 1. Is 2 times the integral from 0 to 1 of x to the power 4 plus 1. It's always easier to replace 1 into the function than replacing 1 and negative 1. What you get is 2 times integral from 0 to 1 of that is basically the antiderivative of x to the 4 is x to the 5 divided by 5 plus antiderivative of 1 is x evaluated from 0 to 1. This is 2 times whatever that number is. Replace 1, it'd be 1/5 plus 1. Replace 0, get minus 0 plus 0, so minus 0. This is the good thing by replacing 0, it becomes simply 0. If you would have evaluated -1, you should have said -1 evaluated, then you didn't need that 2. What you get is 2 times 6/5, which is 12/5. So the integral is simply 12/5. This is since you have an even function. Now, if you look at the next example, it doesn't look like you can evaluate this function, this integral. Very complicated combination of trigonometric and polynomial function over a fraction. Super complicated. Maybe impossible to calculate this integral with what we learn in calculus. Maybe there are other methods by approximation you can evaluate this, or something else, Taylor expansion, whatever. But in this case, for us using substitution, it's definitely not possible. But what we can notice is that the boundaries, -1 to 1, are symmetric. So we say, okay, if I pick the function f to be sine x divided by 1 plus x to the second power plus x to the fourth power, is it the symmetric function? We can evaluate f of -x, you'll get negative sine x divided by 1 plus x squared plus x to the 4th. By replacing negative, these become same thing. Sine of -x is negative sine of x. So you notice that this is the same as negative f of x. Which means the function itself is an odd function. And what we know is, if you have an odd function, whatever this function looks like, maybe something like this, 1, exactly on the other side you will have the same thing, up to -1. So these two areas match up because you have an odd function. So I don't really need to calculate and say, okay, since this is odd over a symmetric interval, this integral must be 0. There's no need to calculate the exact value. Okay, sometimes you have a combination of both. So if you look at this case, if I look at the function f, again, always check first to see if you have a symmetric boundary. If you don't have symmetric boundary, you cannot use any of these information. This information is if only you have symmetric boundary. If I pick the function to be sine cube x plus x squared and say, is it symmetric function? F of -x would be negative sine cube x, but x squared would be positive x squared. So this is not a symmetric function at all. These two are opposite of each other, but these two are equal. That means this x squared is even, while sine is an odd function. So if that's the case, we cannot use the theorem. But you can do this. You can say, okay, I'm not gonna use the theorem there, but I can do this. I can say, I'm gonna break this up into two parts. Integral of sine plus the integral of x squared from -1 to 1. Because I can use the properties of the integral and break it up. What do I know? I know this is an odd function, so the integral of that simply would be 0. So now I don't need to deal with this term. What I just need to calculate is from -1 to 1 x squared dx. And since it's an even function, it's the same as 2 times from 0 to 1 x squared dx. And you notice that it is simply 2 times the integral of x squared is x cubed over 3. Evaluate from 0 to 1. Replacing 1 will give us 2/3. Replacing 0 would be 0, so -0. Just simply 2/3. So sometimes you can break the function into separate pieces, odd, even. Ignore the odd ones because these will disappear. This is supposed to be 0, the integral of that. Again, this is only true if you're dealing with symmetric boundaries. Okay, this is kind of it for this section. it's a very important topic, so try to do as many examples as possible. There are the questions assigned for the homework, but since this is very important, try to pick some examples from the textbook as well and do those. Okay, I'm going to stop at this point. Next time we'll start chapter 5.